Dear colleagues, I am Всеволод Bogoyenko from Institute of Cybernetics in Kiev, and I would like to present you a talk about the decision support system and sprinkler irrigation built on the base of fractional moisture transport model. So, we work in the field of decision support and irrigated agriculture. The need for the development of more and more precise software in this field is determined by climate change and subsequent water scarcity issues. The decision support system here helps to determine optimal schedules and rates of irrigation, increasing water use efficiency. One of the approaches used to determine times and rates of irrigation is to predict the state of soil moisture, taking evapotranspiration estimates as input. In this context, we present a novel decision support system based on the following ideas. At first, we use a fractional differential Richards equation to model moisture content dynamics. Then we select the best linear combination of evapotranspiration estimates. And at the end, we use the particle swarm optimization algorithm to calibrate the model on the base of available measurements. The core of our system consists of the models of moisture content dynamics. As the most complex model, we use the fractional Richards equation stated in terms of water head. This equation contains the fractional order Caputo derivatives that are integral differential operators. The derivatives introduce additional parameters that allow taking into account fractal effects in soil structure. The fractional model is a generalization of the classical Richards equation that can be obtained from it, setting derivatives orders to 1. Additionally to differential models, we also make predictions using a simple balance model of moisture content. In the case when input data, including hydrophysical parameters of soil, can be considered as substantially incorrect. In our system, current state of soil moisture is determined by pressure measuring sensors, and we also monitor soil moisture availability using them. Several parameters greatly influence the accuracy of soil moisture dynamics modeling. The first block of them is the hydrophysical parameters such as water retention curve and the dependency of hydraulic conductivity on water head. They are quite accurately determined by laboratory analysis. The most influencing input that can be only assessed is the evapotranspiration. We use 3 models to estimate it. The first one is the widely applied Penman-Montate method that is hardware implemented in some modern weather stations. The other 2 are the empirical formulas of Ivanov and Stoiko obtained for the conditions of Ukraine. They use only surface air temperature and humidity as inputs, so estimates according to them can be easily calculated on the basis of weather forecast data. To adopt to changing growth conditions, we introduce multipliers for evapotranspiration estimates in the equation of moisture transfer. Then we select their values during models calibration. The third algorithmic block of our system forms the parameters identification algorithm. We use the measured water head values in some period preceding the current moment of time, along with evapotranspiration estimates for this period to select the values of models parameters, the way to minimize sum of square of difference between modeled and measured water head values. These parameters that are identified are fractional derivatives orders, evapotranspiration multipliers values, and precipitation and irrigation fluxes multiplier value. As the parameters have floating point values, and from the best of our knowledge there are no deterministic method to solve such an inverse problem, we use particle swarm optimization algorithm that is a meta-heuristic technique for this purpose. Finally, the algorithm for predicting irrigation schedules and rates have the following stages. At the initialization stage, we perform the calibration of the fractional and integer order differential models. Their recalibration is performed if within a given period the best model describes the measured data with an average relative error more than a given threshold. Then, Once per some given period, we perform predictive modeling of water head dynamics for a given period using the fractional, the classical integer order, and the balance models, and then determine the next irrigation time and rate using the model that best describes the measurements. This algorithm was implemented in web-based software the following way. Field data collected using iMetos or Devis microweather station are acquired once per hour and saved in systems database. The corresponding modules are implemented in Python and PHP as the most other parts of the software. Once a day, the specific modules perform a soil moisture state prediction, and once per 5 days they perform corresponding models calibration. Due to high computational complexity of these procedures, they were implemented in C++ using OpenMP multithreading. Then, the Python implemented module generates recommendations for the users and saves them into the database. The system has several graphical user interfaces for irrigation system operators, agronomists, and system administrators. Two interfaces are implemented for the end users. The first one on the left part of the slide is a compact interface with information needed to perform irrigation. In it, for each field of the farm, a 5-day prediction of weather and soil moisture state is presented along with the recommendations for performing irrigation. The second interface on the right side of the slide gives access to the full amount of data saved in system database. It can be used for administering, for manual adjustment of models calibration parameters, and for agronomic or hydrological research purposes. In conclusion, I want to focus on the merits of our system and the direction of its further development. The implemented algorithmic tools allow to increase soil moisture state prediction accuracy up to 7% when fractional model is used compared to the classical one, and hence to save irrigation water up to 30% according to the results of system's practical usage this year. In future, we plan to implement two-dimensional models that will give an ability to use the system for drip irrigation management. We also plan to widen the support of different input data sources and to decrease the time needed for recommendation generation involving sophisticated parallel computing techniques. Thank you for your attention.